So today we are extending our talk about systems of equations, and now we're going to work with both linear and polynomial. So just starting off with a quick turn and talk that we did in class to kind of engage our thinking. In each of these three photos, how many solutions does each photo have? And if we think about yesterday, it was all about intersections, so spots that our lines intersect, our graphs intersect. In the first one, we get 2 solutions. In the second one, we would have 1 solution. And this third one here, we would have no solutions because there's no intersection there. So again, just rehoning in, our solutions for systems graphically are going to be where our intersections are. So just like we did yesterday, we are going to solve a bunch of problems graphically first, and we're going to use a combination of quadratic and linear equations. So if you go into Desmos and you punch in the equation for, or the 2 equations for system 1 here, you can see that we get a nice quadratic curve, we get a nice line curve, there's our polynomial and linear system. And if we click on either of those lines, some gray dots pull up. I'll zoom in just a little bit more. Those gray dots pull up and we can find our solutions. In this case, this one is at -3 and 2 and -2 and 2. So there is a little more to take care of here. We have 2 solutions. We have -3, 2 and 2, 2. Now, go through and try this for all 4 of these. I'm going to jump to the last one, problem number 4, to just talk about that one as well. And let's go over to Desmos and punch that in. We get x squared plus 3x plus 8. So y equals x squared plus 3x plus 8. And the second equation is y equals x plus 2. If I go there, I might have to do some scrolling out, and you can see it looks like the blue line just clips the red line, so it's tough to tell even if there are solutions. But if I click on either of those graphs, again, Desmos will highlight those intersections. We can kind of zoom into that point, and we'll have a solution at 2, 18 and 3, 26. So our solutions there, 2, 18 and 3, 26. So we are going to kind of, just like yesterday, take what we learned graphically, find out how to do it on paper as well. So first thing I want to do is just jot down what we've learned graphically into our note sheet here. First key point that we want to bring up is the degree of the polynomial is the maximum number of solutions each system can have. So we were dealing with second degree polynomials in our Explore examples. So we had 2 solutions for each of those. But if you look down here in our little chart here, we have a third degree polynomial with that odd behavior. You can see that line through, or the purple line passes through 3 different times. So there's 3 solutions in this case here. Then there's also a scenario where there's 2 solutions. We have the purple line just kind of glancing that third degree polynomial and then passing through. There's also a case where we just have 1 solution, right? Where the line only passes through once. Second key point, and we didn't fit this on our note sheet because we were starting to run out of space here. If there are no intersections, it means no solutions, just like yesterday. If those lines don't intersect, there are no solutions to our system. So to solve these linearly, it is going to follow a slightly different process than what we did yesterday. It starts the same, where we kind of solve and substitute as needed to get one equation with only x's. So you're going to kind of isolate y's, plug in those y's. Then we're going to set one side equal to 0, and we're going to tie in that skill we did with factoring and with finding zeros to help us out. We'll factor that remaining polynomial, and we'll find the zeros from that equation. Let's see how this plays out in an example problem. We get our system is y equals x squared plus 5x plus 8 and y equals 2. We have a degree of 2, so we might have a max number of solutions of 2. But that first step there, solve and substitute to just get an equation full of x's. So I see that both of these are equal to y already. And so what I'm going to do is I'm going to take this y equals 2 equation. I'm going to rewrite it. But instead of writing y, I'm going to write in that red equation there, the y equals x squared plus 5x plus 8. Make sure that looks like a nice and clean x there. So I got an equation in only x's. Now what I want to do is I want to set one side equal to 0. And we're going to see why that's valuable in a second. If I subtract 2 from both sides, that brings that over. We then get x squared plus 5x plus 6 equals 0. The next step tells us to put it in factored form. So if we use our kind of side puzzle, I'll mark this on the side. Don't feel like you have to do it. But we're multiplying to 5. We're adding up to 6. 3 and 2 is a good combination there. So we get a factored form of x plus 3 and x plus 2 equals 0. And the value of setting that equal to 0 there is then we just have a situation where we can find the zeros of the polynomial and get our two different values of x. So the zeros in this case are x equals negative 3 and x equals negative 2. And we can plug this back into our equations to figure out what the y is equal to. But in this case, we actually already know that y is always equal to 2 from one of our equations. So we can take this info and we know that one of our solutions is going to be that negative 3, comma 2, and negative 2, comma 2 as our answers. And again, just like yesterday, we can check this with Desmos. If you go to Desmos and type in those two equations there, you'll notice that, hey, we have a solution at negative 3 and 2, and another solution at negative 2, comma 2. So let's try this. Let's try this with example 2. Very similar scenario where we have two equations equal to y, so we can start by just setting them equal to each other. We'll have x squared minus 9x plus 3 equals negative 5. We can then add 5 to both sides. Get x squared minus 9x plus 8 equals 0. And if we want to factor that out, our two factors would be x minus 8 and x minus 1. And that easily helps us find those zeros there. So we get x equals 8 and x equals 1. So we can use that. We can plug it back in to find our solution. In this case, again, we have another scenario where y is fixed value at negative 5. So our two solutions are 8, comma, negative 5, and 1, comma, negative 5. Let's go check that out in Desmos. So x squared minus 9x plus 3. So x squared minus 9x plus 3, and y equals negative 5. And if I move to those intersection points on our graph or click on a line, we see 1, comma, negative 5, 8, comma, negative 5. That indeed matches what our solutions were there. So moving on to example 3, it is a little more complicated because we have an x in our second term, but we do still have the y's all by themselves. So we can kind of set these equations equal to each other like we did before. X squared plus 7x plus 4 equals 2x. Okay, we can subtract that 2x from both sides, and notice how I'm going to write it underneath the like term in this case to kind of signal that that's what we combine. Get x squared plus 5x plus 4 equals 0. And so now that I'm set to 0 on one side of my equation, I can factor. In this case, we'll have 4 and 1. So x plus 4 times x plus 1 equals 0. And that'll give us zeros or solutions at x equals negative 4 and x equals negative 1. And now, if we plug these back in, we actually have to use this y equals equation, y equals 2x. So in one case, when x equals negative 4, y is going to be equal to negative 8, because we have 2 times negative 4. And when x equals negative 1, our y is going to be equal to negative 2. So our solutions there are negative 4 comma negative 8, parentheses around that ordered pair, and negative 1 comma negative 2. And again, let's check that in Desmos, see if we got that right. X squared plus 7x plus 4, and y equals 2x. And we can click on our lines to find the solutions, negative 4 comma negative 8, and negative 1 comma negative 2. And that looks good, that matches out. Let's do one more example, and then let's call it a day. So if we move to example 4, now we have an even more complicated equation for our second one. The same principles are going to apply as before. We have both equations equal to y, so we can simply set them equal to each other. X squared plus 3x plus 8 equals 8x plus 2. And just like we did before, we can move stuff over to get 0 on the right side of our equation. So if we do that, we move that 2 over by subtracting it. X squared plus 3x plus 6 now equals 8x. Then we could also move that 8x over right after that. Minus 8x minus 8x, and get x squared minus 5x plus 6 equals 0. That will give us a factoring of x minus 3 times x minus 2 equals 0, which means that my zeros there, x equals 3 and x equals 2 for our solutions. We're then going to have to plug it back in, which I'll do this on the side here using my y equals 8x plus 2 equation. So we get y equals 8 times 3 plus 2. So in that case, we get y equals 26. And we also get y equals 8 times 2 plus 2. And that would give us 18. So our two ordered pairs are 3, comma 26, and 2, comma 18. Let's check it out in Desmos before we close this out. Y equals x squared plus 3x is 8. And I believe it's 8x plus 2. Let me double check, make sure I did that right. Yep. Going to zoom out here. Let's see where our solutions are. Oh, this is the one that kind of clips it there. We have 2, comma 18 and 3, comma 26. And those indeed match what we have for our algebra solutions. So important thing is to understand the graphing, but it's good to get exposure to the algebra work as well today. Knock out those practice problems and then take the exit ticket in class.